Welcome to Calculating the pH of buffers. This is also buffers part 2. So if we make sure before you watch this that you have looked over the what makes a buffer and what doesn't make a buffer, because I'm not really going to go over that here. All right, so there are two ways to calculate the pH of a buffer. The one equation that will be provided to you on the AP test is the pH version. So this is called the Henderson-Hasselbalch equation. The pH is equal to the pKa plus the log of A minus over HA. And let's remember that A minus is going to be your conjugate base, and your HA needs to be a weak acid. And these need to be conjugates of each other. You can't have any conjugate base and any weak acid. They have to be a pair of them. So, for example, you would need to have HCN and CN minus, some combination of those. And these would be the values that you would put in. So when you actually put it into the equation, the CN minus would go here, and the HCN would there. I'm just showing you here that this would be the weak acid conjugate base pair that you would need to create a buffer. And the Ka value that you would use is always going to be based on the weak acid. So it's kind of confusing as to whether you would use a Ka or Kb in all of these problems, because you have both an acid and a base. You have to have both an acid and a base to have a buffer. If you are starting with a weak acid, so if you either have a weak acid or its conjugate base, so some sort of anion that comes from a salt that you're going to be using. With either of those, no matter whether you start with the conjugate base or you start with a weak acid, you're going to start with the pKa. It's just easier to plug into the equation that way, because if we remember, if you go to look up the value for HCN and CN minus, you're only going to find a value for HCN. This is the only one you're going to find a value for. There's nothing in a table for this. So if what you can find is the pKa of this, or at least the Ka of this, go ahead and use this, because otherwise you've got to convert and everything just gets confusing. The other equation, and this mirrors it, is going to be the POH equals pKb plus the log of BH plus over B. So we remember that BH plus is going to be your conjugate acid. So it's got a positive charge. All conjugate acids will have a positive charge. And B will be equal to your base. So an example of this would be, I'll write the conjugate acid first. So that would be NH4 plus, okay, and then that would be over your base. The base that it belongs to is NH3, ammonia. So this would be your conjugate acid base pair. The reason why you would want to use the pKb for this is because when you go to look up the value for the Kb, you're only going to find, and I know in this case you actually can find it for the other, but usually you're only ever going to be able to find the pKb. So if the value you can find is the pKb, then, or the Kb, then it's going to be easier to base all your calculations with this. And we'll see this in some practice problems in this podcast and then in an extra practice session. So let's take a look at a very basic example. Example number 1. We have 40 milliliters of 0.2 molar HNO2, and we're going to mix that with 60 milliliters of 0.1 molar KNO2. So in this case, we're not going to have a chemical reaction. We have here a weak acid, and we have here its conjugate base, or a salt containing its conjugate base. Remember, K plus is going to dissolve, and you're going to end up with NO2 minus. K plus is a spectator ion. So in order to solve this equation, what you're going to need to do is to take these and convert them into moles, because when you add two volumes together, their molarities are going to change. So if we take the two of these and multiply them, we will have 0. So this is 0.04. You're going to have 0.008 moles of HNO2. And when I take these two, I'm going to end up with 0.006 moles of NO2 minus, because remember, I don't really care about the K. And we'll just plug it into the equation. So pH equals the pKa. So pKa means negative log. And the Ka value for this one is 4 times 10 to the negative 4. I just looked that up on the chart. Plus the log of, so this is going to be my A minus, this is going to be my HA. So I'm going to have the log of HA, which is 0.008 over 0.006. And now it's just a matter of plugging it into the calculator. All right, and when I plug it into the calculator, I get the pH is equal to 3.52. Remember with this, I know in this case we're starting with a weak acid, and we did the pH calculations and we got that it was acidic. However, you can, with a weak acid, get a pH that is above 7 because you have both a weak acid and a conjugate base. So it depends on which one is stronger. They're both weak, but one's going to be a little bit stronger than the other. So in this case, this shows us that the weak acid is actually stronger than its conjugate base. All right, so we have an example here where we have a weak base and we have a salt containing the conjugate acid of it. So we're getting rid of the Cl minus because we know that's a spectator. So this is going to be a conjugate acid. All right, so what we're going to need to do here is we're going to need to convert these into moles. So if I take this, and if you had a case where they gave it to you in moles, like this many moles was added to this many, you would just be able to skip this step. But when they give you the volume and they give you the molarity, you have to multiply it out. So you've got 0.005 moles of your weak base, and you would have 0.005 moles of NH4 plus because we don't care about the Cl minus. All right, so in this case, we're going to want to use the POH because we have a weak base, and that is what we have the pKb value for. So we're going to start with POH equals the negative log, because that's the P value of the Kb, and the Kb in this case is 1.8 times 10 to the negative 5 plus the log. So this is going to be my BH plus this is going to be my B. So it's going to be 0.00. I'm going to run out of room here. There we go. I'll write it this way. Okay. And this is a special case when your two moles are equal to one another. So when you have the exact same number of moles of your conjugate acid and your base, this factor here will equal 0. So you actually don't have to include it. So your POH will directly equal your pKb. So we really could have even skipped that step here. So now it's just a matter of plugging it into the calculator. All right, so I found out that the POH was 4.7, make that a little bigger, 4. So that would make my pH 14 minus that. So we would get the pH would equal 9.26. And again, remember, even if you're starting with a weak base, okay, if you're doing all your calculations for POH, you have conjugate acid in there. This value here can actually be below 7. It depends on which one is stronger. The fact that this pH is basic means that your weak base is stronger than your conjugate acid. That's what it's letting us know, okay? All right, so let's do one more example problem here. So in this problem, we have 60 mils of HNO2 and we have 20 milliliters of 0.1 molar NaOH. In this case, I have a weak acid, and to this, I'm going to add a strong base. So when we see that here, we obviously don't immediately have a conjugate base. But this is going to force this to form the conjugate base. And if you're confused about that, go back and watch the first buffer video. So what this is going to do is the weak acid is going to react with the OH. And the reaction is only going to go in one way. Okay, it can only produce a Ford's reaction because this is a strong base. And it's going to produce the conjugate base and water. All right, so we have... So I'm going to go back and look at our values here and convert these into moles. So I have 0.006 moles of this to start with, and I have 0.002 moles of this, and relatively none of that. So all of this is always going to be my limiting, this one here, the OH, it's going to be my limiting reagent. It's going to get completely used up. Because if I added too much OH, I wouldn't have a buffer at all. I would have just a base. So if it's a buffer, that's got to be the one to run out. Otherwise, you have something else. So these are going to get used up, and we're going to add what we use of that. We're going to make of this. We also make water, but we have lots of water in solution, so we don't really care about the water so much. This gets used up, my limiting reagent. Okay, so now this is my weak acid. And my weak acid is my HA, and this is my conjugate base. That's my A minus. I'm writing a lot of stuff on here. And now all we need to do is plug it into the equation. And so we will have the pH equals the pKa, and since we used, the same Ka, same problem as before, we know that that's 4 times 10 to the negative 4 plus, and you just look that up on the table to know this value, plus the log of, we always use A minus, so that's 0.002 over HA, that's 0.004. Okay, and now it's just a matter of plugging it into the calculator. Okay, and so I get my pH is equal to 3.10. And if you're a little bit confused, if you kind of lost me at this step, these numbers, by the way, the values that I'm getting here, were just these converted into moles. So this times this equals 0.006 moles, and this would be 0.002 moles. And I had just plugged those in here. And if we look at the pH, what's kind of interesting is we solved a very similar problem in problem number 1, and we found the pH to be very similar, because a buffer system is going to come up with a very similar answer, because the whole purpose of a buffer is that it resists the change in pH. So it's going to have a very similar pH, and that's why we're seeing a very similar answer here. It's not exactly the same, but it's around the same pH. If you watch the next video, I'm going to go through another series of practice problems, but I don't want this video to get too long. So open up the next practice problem to see some more.